Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine dropping this massive boulder into a bottomless pit.
Right. You expect it to just fall silently into the dark and, vanish from existence forever.
Exactly. But instead of that quiet disappearance, the pit suddenly violently spits half of that boulder back out.
Just launches the shattered pieces straight back at your face at nearly the speed of light.
Right, which completely breaks the rules of how a pit is supposed to work.
Yeah.
I mean, it's totally backwards.
Yeah.
But, everything you thought you knew about black holes being the universe's ultimate unstoppable vacuum cleaners is essentially that broken rule.
It really is. I mean, we've been working with this very compelling but ultimately flawed archetype for a really long time. The perfect cosmic drain.
Yeah, the trapdoor in space.
Exactly. It's a neat, terrifying concept. You get too close, you cross the event horizon, and boom, you are deleted from the universe.
Just gone.
Right. But gravity at that extreme scale is actually far more chaotic and, frankly, far more creative than just a simple point of no return. We're discovering that black holes don't just consume matter, they actively redistribute it.
So today, we are taking a sledgehammer to that old vacuum cleaner myth. We're unpacking some recent, highly detailed astronomical observations, specifically focusing on this groundbreaking research from Dr. Noel Castro-Segura, along with data pulled directly from the Very Large Telescope.
And this data completely reshapes how we understand these objects.
Totally. We're moving away from the bottomless pit idea and looking at a reality where a black hole acts much more like a highly complex, incredibly messy cosmic digestive system.
And, the paradigm shift here is profound. I really want to emphasize that this is not just some slight mathematical correction to an obscure theoretical model.
Right, it's much bigger than that.
Huge.
Mm-hmm.
When we observe a black hole feeding now, we're seeing it actively alter its surrounding environment in real time.
Like literally watching it happen.
Yes, we are capturing the mechanical anatomy of that process on a very granular level. It fundamentally changes our understanding of the whole life cycle of galaxies.
Okay, so to see this in action, we're going to look at a spectacular event from 2023. Astronomers were watching this newly discovered black hole system, which goes by the incredibly catchy name Swift J1A1027.8 Jude 1613.
Rolls right off the tongue.
Oh, yeah. Let's just call it Swift J1727 for our sanity. But this system gave us an unprecedented front row seat to the sheer violence of a feeding frenzy. And I cannot wait to get into the mechanics of this.
It's fascinating.
Because the sheer concept of the universe's ultimate trapdoor actively blasting matter back into space, it just hurts my brain a little bit.
I mean, it forces a total reevaluation of basic gravitational intuition. We're so used to thinking of gravity purely as an attractive force, right?
Yeah, things pull other things towards them.
Exactly.
Yeah.
But when you compress enough mass into a small enough space, that attraction creates these secondary effects that are, ironically, violently repulsive.
Wow. Violently repulsive.
Yeah. And Swift J1727 gave us a highly detailed, basically undeniable visual record of those secondary effects. We are essentially looking at the mechanics of a cosmic meal, all the way from the initial intake of material to the final, incredibly powerful expulsion.
Okay, so before we talk about how a black hole spits anything out, I feel like we have to talk about how it gets the food in the first place.
Right, the intake.
Yeah, because it's not just wandering through space, gobbling up random planets like Pac-Man, right? Swift J1727 is a binary system.
Yes.
So we have this black hole, and it's locked in this intense gravitational dance with a companion star.
And that proximity is what dictates absolutely everything that follows. You have a relatively normal star, perhaps something similar in composition to our own sun.
Okay.
And it's orbiting dangerously close to a stellar mass black hole.
Dangerously close being the operative phrase.
Exactly. The black hole's gravitational pull is immense. It's so powerful that it creates this massive tidal force stretching across the space between them, and it's actively overpowering the companion star's own internal gravity.
So it's literally peeling the outer layers of the star off, like an onion.
A very hot, gaseous onion, yes.
That is such a wild visual.
It is. The outer envelope of the companion star actually gets deformed. It's stretched into this teardrop shape that points directly toward the black hole.
Oh, wow.
Yeah, and the gas at the tip of that teardrop reaches a critical point where the gravitational pull of the black hole exactly equals the pull of the star.
Like a tug of war that's perfectly tied.
Right. But once the gas crosses that threshold, the tie is broken, it belongs to the black hole. It just begins to free fall through the vacuum of space.
Okay, and in 2023, this process suddenly hit a breaking point, right?
Yeah.
Swift J1727 just erupted.
That was a massive event.
Yeah, it went from being essentially this dark, quiet patch of sky to suddenly becoming one of the absolute brightest X-ray sources we could see anywhere. Just a massive, violent flare-up.
Truly blinding in the X-ray spectrum.
But, okay, here is where the visuals get a bit tricky for me, and I want to unpack this. If a black hole is completely black-like, by definition, because its gravity traps all light, how does it suddenly become a blinding source of X-rays?
That's a great question.
It feels like a total contradiction.
Yeah.
You know, it can't be the black hole itself that is shining.
No, it isn't. You really have to separate the black hole, which is the actual singularity and its event horizon, from the environment immediately surrounding it.
Yeah.
So the light is not coming from inside the house, so to speak.
Right.
It's coming from the front porch. When that gas is stripped away from the companion star, it does not fall straight down into the black hole.
Because everything in space is moving, right?
Yeah.
The star is orbiting the black hole, so the gas it sheds already has sideways momentum.
Precisely. It has orbital momentum, so instead of a straight vertical plunge, the gas spirals inward. It forms this vast, flattened structure known as an accretion disk.
Okay, an accretion disk.
Yeah, think of water swirling around a drain, but, moving at a significant fraction of the speed of light.
See, I picture it more like a cosmic blender running on the highest possible setting.
Oh, I like that.
Yeah, you have all these ingredients, this stellar gas being dumped into the bowl, but because it's swirling inward so incredibly fast, the particles of gas are constantly smashing into one another.
Exactly. The friction is immense.
Right, it's the friction of those ingredients rubbing together inside the blender that creates the heat long before the material ever actually reaches the blades in the center.
The blender analogy is an excellent way to conceptualize the thermodynamics at play here. The extreme physics of the superheated disk are honestly difficult to overstate.
Like, how extreme are we talking?
Well, we are not talking about a warm, glowing fire. The friction and the gravitational compression within that spiraling disk are so intense that the gas is literally stripped of its electrons.
Whoa.
Yeah, it ceases to be normal gas and becomes a plasma.
Which means it's incredibly hot. Like, numbers-wise, how hot is that?
Millions of degrees.
Millions.
The inner edge of that accretion disk, just before the matter crosses the event horizon, reaches temperatures that would make the core of our sun look tepid.
That is just, I can't even fathom that.
It's mind-boggling. And when matter gets that hot, it radiates massive amounts of energy, predominantly in the high-energy spectrum of X-rays.
Oh, okay. So that is what lit up our detectors in 2023.
Exactly. We were not seeing the black hole. We were seeing the catastrophic friction of the meal being prepared.
The meal being prepared. I love that. And this wasn't just like a quick flash that astronomers noticed after the fact, right?
No, not at all.
They actually tracked this feeding process as it happened in incredible detail using the European Southern Observatory's Very Large Telescope, the VLT.
And, the involvement of the VLT is really what elevated this event from a routine observation to a massive breakthrough.
How so?
Well, historically, monitoring these black hole outbursts is a game of catch-up. Telescopes sweep the sky, they notice a sudden spike in X-rays, and by the time we actually point our most powerful optical instruments at the source, it's over.
Basically, we're only catching the aftermath, or perhaps just an isolated snapshot of the peak if we're lucky.
It's like trying to piece together the plot of an entire movie by looking at 3 blurry Polaroids scattered on a table.
A very apt comparison. You missed the progression. But with Swift J1727, the astronomical community coordinated with remarkable speed.
That's awesome.
It was. The VLT in Chile, which is one of the most advanced optical and near-infrared telescopes on the entire planet, was able to compile an extraordinarily detailed, high-quality record of the whole event.
So they basically got the whole movie this time.
Exactly. They watched the accretion disk evolve, they tracked the shifting temperatures, the change in velocities of the gas, and the varying light outputs across multiple distinct stages of the outburst.
Man, let's just pause and visualize the sheer terrifying scale of this for a moment.
It's worth taking a moment for, absolutely. Imagine standing on a hypothetical planet a safe distance away. You have a star, a massive boiling sphere of plasma, and it is being agonizingly siphoned off. This river of material is being dragged across millions of miles of empty space, wrapping around this invisible point of infinite darkness.
Beautifully terrifying.
And it spins so violently that it outshines entire galaxies in X-ray vision. It's this unimaginably destructive force, but when you describe the physics, it's also functioning like a beautifully complex engine.
You know, an engine is the perfect mechanical framework for this.
Really?
Absolutely, because any functional engine requires moving parts. It requires an intake of fuel, a combustion process, and critically an exhaust system.
The exhaust. Okay, this is where the story of Swift J1727 completely pivots, doesn't it?
Absolutely does.
Because we have this vivid image of this blinding, superheated disk of stellar material swirling inward, preparing to be completely devoured by the event horizon.
The ultimate meal.
Right. But the massive surprise in the VLT data, the real twist here, is that a huge portion of that meal never actually goes down the drain.
No. And the data revealed something that directly contradicts that whole vacuum cleaner assumption we talked about earlier.
Okay, so what actually happens?
Simultaneous to this immense volume of matter spiraling inward, the black hole began launching incredibly powerful jets and winds, physically throwing material back outward into interstellar space.
This is the part that just shatters the old myths for me. This isn't a pristine, efficient machine vacuuming up dust.
Not even close.
It is far more like a messy toddler sitting in a high chair eating a bowl of spaghetti. Half of the pasta makes it into the mouth, but the other half gets violently thrown across the kitchen in every possible direction.
While Dr. Noel Castro-Segura prefers the term cosmic digestive system, I have to admit, the messy toddler analogy captures the chaotic mechanics perfectly.
It just makes so much sense.
It does. Dr. Castro-Segura highlighted a crucial misconception in his research. People assume black holes just swallow everything indiscriminately, but this real-time observation proved that the system processes the matter.
And a staggering amount of that processed material is expelled again.
Exactly.
When we say a staggering amount, though, we aren't just talking about a few stray particles of dust escaping the gravitational pull, right? Like, how much of the star's gas is actually being thrown at the walls?
The amount of material blasted back out into the cosmos is comparable to the amount the black hole actually consumes.
Wait, comparable? Are you saying it's nearly a 1-to-1 ratio of eating to throwing food away?
Depending on the specific stage of the outburst, yes.
That is insane.
It is an extraordinarily inefficient consumption process. But to understand why it throws the food, we really need to unpack that cosmic digestive system concept.
Because digestion implies a transformative process.
Precisely. The black hole is an active transformer of matter. The VLT data revealed a direct, measurable causality between the changes happening in that inward swirling feeding disk and the launching of the outward jets.
So the act of the gas falling inward is what physically causes the other gas to be shot outward. How does that even work? I mean, gravity is pulling it in. What force is strong enough to reverse that pull and shoot it away at nearly light speed?
Magnetic fields.
Magnetic fields.
Yeah. And to understand this, we have to look closely at the nature of the plasma in the accretion disk. Because the gas is superheated into a plasma, as we discussed, it is highly electrically charged.
Okay, right. Electrons are stripped away.
Exactly. And moving electrical charges generate magnetic fields.
Okay, so the accretion disk is basically a giant spinning electromagnet.
Yes, exactly. Now imagine twisting a rubber band attached to the propeller of a toy airplane.
Okay, I'm picturing it.
As the gas in the accretion disk spirals closer and closer to the black hole, it is moving faster and faster. This rapid rotation grabs those magnetic field lines and begins to twist them, winding them up incredibly tight around the rotational axis of the black hole.
So the tension is just building and building as the disk spins.
Exactly. It winds tighter and tighter until the magnetic tension reaches a critical threshold where it simply can no longer hold.
And then what? It snaps.
Yes. The twisted field lines violently snap and reconnect. When that rubber band snaps, it releases a monumental amount of stored magnetic energy.
Wow.
And this snapping physically grabs a massive portion of the infalling gas away from the event horizon, accelerates it along the newly aligned magnetic poles, and blasts it out as narrow, highly focused jets.
That is unbelievable. It is literally using the gravitational energy of the falling matter to build a magnetic cannon, just to shoot the rest of the matter away.
That is the exact mechanism. The intake of fuel directly powers the exhaust. It completely replaces the archetype of the unstoppable glutton with a dynamic, self-regulating engine.
That is deeply fascinating. It's a self-regulating system.
Totally.
But the timeline of this exhaust system is where things get truly bizarre to me.
Yes, the timeline.
Because logic would dictate that this violent expulsion, the magnetic cannons, the toddler throwing the spaghetti, would only happen during the absolute peak of the frenzy.
That's what you would intuitively think.
Yeah, like when the cosmic blender is running at maximum speed and those X-rays are blindingly bright. But the biggest shock of the entire swift J1727 event happened after the lights essentially went out.
The grand finale of this outburst provided the most critical piece of the whole puzzle. It really forced us to confront our own observational biases.
Let's walk through that finale because it's wild.
Right.
So the astronomers are watching this system. The initial feeding frenzy starts to die down. The companion star isn't being siphoned quite as aggressively.
Right.
The accretion disk starts to cool off, and the overall system becomes extremely faint. I mean, the data showed that it dimmed to roughly 1/100th of its peak X-ray activity.
Just 1% of its maximum brightness.
Right. So to our X-ray telescopes, it looked like the dramatic event was basically over. The black hole was satiated, the engine was cowering down, and the system was returning to a state of dormancy.
But even in this incredibly faint, quiet state, the researchers detected something massive. They discovered that dense, relatively cool gas was still being blown away from the accretion disk in the form of incredibly powerful, sustained winds.
Wait, winds? Not the jets from the poles?
No, not the narrow, light-speed jets from the poles. This was a broader, massive outflow of material.
Okay, I am going to throw a flag on the play here, because this physics problem really stumped me.
Oh, let's hear it.
If the X-ray brightness, which we established, is the direct result of the friction and the energy of the feeding frenzy drops to just 1% of its peak, how does the black hole still have the juice to push massive amounts of dense gas into space?
It's a fantastic question.
Like, if the intake powers the exhaust, doesn't the engine need a roaring fire to keep pushing that much heavy material? How is it generating massive winds when the X-rays suggest the engine is essentially turned off?
That apparent contradiction is precisely what makes this paper so revolutionary. It forces astronomers to completely separate radiant energy from mechanical energy.
Okay, you're losing me. What is the difference in this context?
Well, we have historically relied heavily on radiant energy, the X-rays, the visible light, the things our telescopes can easily see, to tell us how active a black hole is.
Sure, bright means active.
Exactly. The intuitive assumption is that bright equals powerful and dim equals weak. But this late-stage massive expulsion proves that the mechanical power of the system, the sheer kinetic force pushing matter around, operates on a much longer, much more resilient timeline than the radiant output.
Oh, I see. Are we talking about momentum?
Partially, yes.
Like a spinning top. Even if you stop actively twisting a toy top, which would be the radiant energy dying down, it doesn't just stop dead. It keeps spinning for a long time purely because of the momentum it built up.
That is a brilliant analogy. Yes, we are absolutely talking about residual angular momentum and latent magnetic tension. The radiant emission, the glowing friction of the plasma, drops rapidly as the density of the inner disk decreases.
There's less stuff rubbing together.
Right. But the mechanical system, the broader outer accretion disk, still retains an enormous amount of kinetic energy and magnetic structure.
So it's still moving, even if it's not glowing.
Exactly. Kyle Solomons, a doctoral researcher who was deeply involved in analyzing this data, pointed this out beautifully. He noted that as observers, we naturally gravitate toward the dramatic, bright fireworks at the start of an outburst.
Sure, it's human nature to look at the brightest light.
But he argues we're basically missing the point by looking away when it gets dim.
Wow.
Yeah. Solomons emphasizes that the finale can be just as intense as the beginning, just in a completely different physical manifestation. The energy shifts from producing blinding light to producing heavy, mechanical winds.
So even though the blender isn't glowing bright enough for us to see the friction anymore, the blades are still spinning fast enough to generate a hurricane inside the bowl.
A cosmic hurricane of dense gas, yes. And this discovery highlights the sheer resilience of these outflows. It fundamentally rewrites our classification of black hole states.
In what way?
It means that even a quiet or dim black hole, one that appears completely dormant in X-ray surveys, might still be an active, forceful presence in space.
That's kind of creepy.
It is. It is still exerting a massive physical influence, physically bulldozing its surroundings with dense winds long after the visible fireworks have faded into the background.
There is something almost haunting about that visual.
Definitely.
This invisible, silent giant just sitting in the dark of space, still exhaling this massive, heavy cosmic wind.
Yeah.
And we've just been completely ignoring this late-stage activity for decades simply because we were only tuning our instruments to look for the bright flashes.
And that specific oversight has skewed our mathematical models of the universe for a long time.
Really?
Yes, which brings us to the most vital part of this discussion, the broader implications.
Right, because astronomy is never just about one isolated object. It's always about the ripple effect.
Always. We have established how Swift J1727 fed, how it threw a massive percentage of that matter outward during the blinding peak, and how it continued to mechanically exhale dense gas even as it faded to black.
Right.
Now we must zoom out and look at the whole chessboard.
So what does this single messy eater imply for the grander cosmic ecosystem? I know the researchers coined a term for this behavior that I think perfectly frames the discussion. They stated that this data proves black holes are highly inefficient eaters.
It is the perfect scientific descriptor.
It really is.
Because they continue shedding material long after their largest outbursts have visually concluded, and because they expel an amount of mass that is roughly comparable to what they successfully consume, they are terribly inefficient at actually gaining weight from their meals.
Right, they're on a cosmic diet.
Pretty much. A highly significant fraction of the stellar material that gets permanently drawn away from the companion star never crosses the event horizon.
So if you are listening to this right now, you might be asking yourself, okay, this is a really cool story about a star millions of light years away, but why should I care if a black hole is an inefficient eater? How does this affect anything else?
It's a fair question.
Let's connect the dots. You, me, the Earth, the cup of coffee on your desk, everything we interact with is made of ordinary matter. Atoms. For a century, popular culture and even introductory physics taught us to think of black holes as cosmic trash compactors. They lock matter away permanently. They literally remove atoms from the universal game board.
Right, the deletion of matter.
But if they are actually inefficient eaters, if they're cosmic recyclers, it means they are actively seeding their host galaxies with heavily processed, energized material.
Exactly. They are taking raw, relatively dormant gas from a companion star, pulling it into these extreme environments, superheating it, magnetizing it, altering its elemental structure through extreme friction.
All the blender stuff.
Right, and then blasting it back out into the interstellar medium at tremendous velocities.
They're basically refining the raw material and shipping it back out.
Yes.
So how does that change the way astronomers look at a galaxy as a whole?
Well, Dr. Castro-Segura pointed out that this explicitly changes our baseline understanding of how binary star systems evolve, for starters.
Okay, how so?
Previously, when astronomers ran computer models of a system containing a star and a black hole, they relied on a principle of clean transfer. They assumed that the mass leaving the star was entirely accreted by the black hole.
Like object A loses 10 pounds, object B gains 10 pounds. Simple math.
Exactly, a clean, closed system. But if mass isn't just transferring, if up to 50% of it is being violently relocated across the interstellar medium through jets and winds, then the gravitational dynamics of that entire binary system evolve completely differently than our classical models predicted.
That makes total sense. Because the black hole isn't getting as heavy as we thought.
Right. The black hole does not grow its mass nearly as fast as we assumed, which means the orbital distance between the star and the black hole changes at a different rate. The lifespan of the companion star is altered. Everything shifts.
Wow. And all that expelled gas, those highly energized winds and jets, they don't just fly through empty space forever, right?
No, they don't.
Because space isn't entirely empty. They have to eventually slam into something.
Yes, they do. They slam into the interstellar medium, the vast, sprawling clouds of cold gas and dust that drift between star systems.
Okay.
And when a jet of plasma moving at a fraction of the speed of light or a massive dense wind carrying the momentum of a star impacts those cold clouds, it creates colossal shock waves.
Like a sonic boom moving through a cloud of dust.
Precisely. And these shock waves can have two wildly different but equally crucial effects on the galaxy.
Okay, what's the first one?
On one hand, the shockwave can compress a loose cloud of cold gas. It forces the molecules so close together that their own gravity takes over, the cloud collapses, and it triggers the birth of an entirely new star system.
Wait, really?
Yes.
So a black hole violently spitting out its food can actually be the spark that creates a new star.
It is a profound catalyst for stellar nurseries.
That is incredible.
It is. But on the other hand, If the outflow is violent enough, or if the galaxy is small enough, these black hole winds can hit the interstellar gas with such devastating force that they physically blow the gas right out of the galaxy, dissipating it into the intergalactic void.
Ah, wow.
Yeah. And without that cold gas, the galaxy can no longer form new stars. The black hole essentially sterilizes its own neighborhood.
That is just... It's a lot to wrap your head around. They have the power to ignite new life and the power to completely shut down the growth of an entire galaxy.
Exactly. They aren't just these passive endpoints of destruction waiting in the dark. They are active, aggressive architects of their environment.
That is the philosophical shift we really must embrace. The beauty of observing this cosmic digestive system is that it paints the black hole not as an isolated monster sitting in the dark, but as a vital, interacting, regulating organ within the anatomy of a galaxy.
A perfect way to phrase it.
By drawing gas inward and returning a substantial portion of it through these powerful outflows, they are regulating the mass and the star-forming potential of their host galaxies. They are deeply mechanically connected to the life cycle of every star around them.
It completely flips the narrative.
The vacuum cleaner metaphor is just dead and buried at this point.
Thoroughly debunked.
So, just to recap this incredible journey we have been on today, we started by looking at a massive, blinding X-ray eruption in 2023 from the binary system Swift J1727.
Right.
We looked closely at the superheated accretion disk, millions of degrees hot, and realized that instead of a clean, silent drain, it was acting like a messy cosmic toddler.
Throwing its pasta.
Exactly. It was twisting magnetic fields to use the energy of its own meal to build a cannon, throwing powerful jets of matter back out into space.
Yes.
Then we saw that even when the lights went out and the radiant X-ray energy dropped to a tiny fraction of a percent, the black hole was still utilizing residual mechanical momentum to generate massive, heavy winds of dense gas in the absolute dark.
Which is honestly a powerful testament to the fact that in astrophysics, the things we cannot easily see, the dark mechanical winds, the invisible magnetic tension, are often just as crucial, if not more so, than the bright, radiant fireworks that initially catch our attention.
It's a great reminder.
It reminds us that there is always more depth to uncover, and that our initial assumptions, no matter how cleanly they fit into a textbook, must always be subject to the rigorous scrutiny of new observation.
It really is the ultimate cosmic recycling program.
Yeah.
And it just makes the universe feel so much more connected, so much more dynamic, and honestly a whole lot messier than we ever gave it credit for.
It is wonderfully messy. And, it leaves us with a rather profound physical concept to consider.
Yeah. Oh.
Well, we know that these black holes have spent billions of years operating as these incredibly inefficient eaters.
Right.
They have spent eons stripping stars, superheating the stolen gas in blinding accretion disks, magnetically processing it, and then violently spitting immense amounts of that transformed matter back out into the cosmos through these massive winds.
Okay, I see where you're going.
If they have been seeding the galaxies with this recycled material since the dawn of the universe, it raises a deeply personal question.
Let's hear it.
How much of the ordinary matter floating in our solar system today, perhaps even the very carbon atoms that make up the chair you are sitting on, or the oxygen you are breathing right now, how much of it once swirled on the very precipice of a black hole?
Wow.
How much of your immediate environment was once bathed in the blinding X-rays of an accretion disk, hanging on the edge of the event horizon, only to be rejected at the last possible second, blasted back out into the void, to eventually wander through space and become you?
Now that is a thought that will keep you awake at night. The idea that we might literally be talking collections of recycled black hole leftovers.
It's entirely possible.
We aren't just made of star stuff. We might be made of the stuff the black hole decided to spit out. That is incredible. Well, thank you all so much for joining us on this amazing journey today. We love pulling apart these cosmic mysteries with you, tearing down the old myths, and seeing what the real mechanics of the universe actually look like.
It's been a blast.
We absolutely cannot wait to see what wild realities the cosmos throws at us next. Until then, keep looking up and keep questioning absolutely everything you think you know.